In geometry, a torus is a surface of revolution generated by revolving a circle in three-dimensional space about an axis coplanar with the circle. If the axis of revolution does not touch the circle, the surface has a ring shape and is called the torus of revolution. Real-world examples of toroidal objects include inner tubes, swim rings, and the surface of a donut or bagel. A torus should not be confused with a solid torus, which is formed by rotating a disk, rather than a circle, around an axis. A solid torus is a torus plus the volume inside the torus. Real-world approximations include donuts, vadi or vada, many lifebuoys, and O-rings. In topology, a ring torus is homeomorphic to the Cartesian product of two circles, S1 times S1, and the latter is taken to be the definition in that context. It is a compact two-manifold of genus 1. The ring torus is one way to embed this space into three-dimensional Euclidean space. But another way to do this is the Cartesian product of the embedding of S1 in the plane. This produces a geometric object called the Clifford torus, a surface in 4 space. In the field of topology, a torus is any topological space that is topologically equivalent to a torus. Geometry. A torus can be defined parametrically by, where theta, phi are angles which make a full circle, so that their values start and end at the same point. R is the distance from the center of the tube to the center of the torus, R is the radius of the tube. R is known as the major radius, and R is known as the minor radius. The ratio R divided by R is known as the aspect ratio. A donut has an aspect ratio of about 2 to 3. An implicit equation in Cartesian coordinates for a torus radially symmetric about the z-axis is or the solution of f equals 0, where algebraically eliminating the square root gives a quartic equation. The 3 different classes of standard tori correspond to the 3 possible aspect ratios between R and R. When R greater than R, the surface will be the familiar ring torus. R equals R corresponds to the horn torus, which in effect is a torus with no hole. R less than R describes the self-intersecting spindle torus. When R equals 0, the torus degenerates to the sphere. When R, the interior of this torus is diffeomorphic to a product of an Euclidean open disk and a circle. The surface area and interior volume of this torus so easily computed using Pappus's centroid theorem, giving these formulas are the same as for a cylinder of length 2 pi r and radius r, created by cutting the tube and unrolling it by straightening out the line running around the center of the tube. The losses in surface area and volume on the inner side of the tube exactly cancel out the gains on the outer side. As a torus is the product of 2 circles, a modified version of the spherical coordinate system is sometimes used. In traditional spherical coordinates there are 3 measures, r, the distance from the center of the coordinate system, and theta and phi, angles measured from the center point. As a torus has, effectively, 2 center points. The center points of the angles are moved. Phi measures the same angle as it does in the spherical system, but is known as the toroidal direction. The center point of theta is moved to the center of r, and is known as the poloidal direction. These terms were first used in a discussion of the Earth's magnetic field, where poloidal was used to denote the direction toward the poles. In modern use these terms are more commonly used to discuss magnetic confinement fusion devices. Topology. Topologically, a torus is a closed surface defined as the product of 2 circles, S1 times S1. This can be viewed as lying in C2, and is a subset of the 3-sphere S3 of radius square root 2. This topological torus is also often called the Clifford torus. In fact, S3 is filled out by a family of nested tori in this manner, a fact which is important in the study of S3 as a fiber bundle over S2. The surface described above, given the relative topology from R3, is homeomorphic to a topological torus as long as it does not intersect its own axis. A particular homeomorphism is given by stereographically projecting the topological torus into R3 from the north pole of S3. The torus can also be described as a quotient of the Cartesian plane under the identifications tilde tilde, or, equivalently, as the quotient of the unit square by pasting the opposite edges together, described as a fundamental polygon AB-1B-1. The fundamental group of the torus is just the direct products of the fundamental group of the circle with itself. Intuitively speaking, this means that a closed path that circles the torus whole, and then circles the torus body, can be deformed to a path that circles the body and then the whole. So, strictly latitudinal and strictly longitudinal paths commute. This might be imagined as two shoelaces passing through each other, then unwinding, then rewinding. If a torus is punctured and turned inside out, then another torus results, with lines of latitude and longitude interchanged. This is equivalent to building a torus from a cylinder, by joining the circular ends together, in two different ways. Around the outside like joining two ends of a garden hose, or through the inside like rolling a sock. Additionally, if the cylinder was made by gluing two opposite sides of a rectangle together, choosing the other two sides instead will cause the same reversal of orientation. The first homology group of the torus is isomorphic to the fundamental group. Two-sheeted cover. The two torus double covers the two-sphere, with 4 ramification points. Every conformal structure on the two torus can be represented as a two-sheeted cover of the two-sphere. The points on the torus corresponding to the ramification points are the Weierstrass points. In fact, the conformal type of the torus is determined by the cross ratio of the 4 points. N-dimensional torus. The torus has a generalization to higher dimensions. The n-dimensional torus, often called the n-torus or hypertorus for short. Recalling that the torus is the product space of two circles, the n-dimensional torus is the product of n circles. That is, the one torus is just the circle. T1 equals S1. The torus discussed above is the two torus, T2, and similar to the two torus, the n torus, Tn can be described as a quotient of Rn under integral shifts in any coordinate. That is, the n torus is Rn modulo the action of the integer lattice zinc. Equivalently, the n torus is obtained from the n-dimensional hypercube by gluing the opposite faces together. An n torus in this sense is an example of an n-dimensional compact manifold. It is also an example of a compact abelian Lie group. This follows from the fact that the unit circle is a compact abelian Lie group. Group multiplication on the torus is then defined by coordinate-wise multiplication. Toroidal groups play an important part in the theory of compact Lie groups. This is due in part to the fact that in any compact Lie group G1 can always find a maximal torus, that is, a closed subgroup which is a torus of the largest possible dimension. Such maximal tori T have a controlling role to play in theory of connected G. Toroidal groups are examples of protori, which are compact connected abelian groups, which are not required to be manifolds. Automorphisms of T are easily constructed from automorphisms of the lattice zinc, which are classified by invertible integral matrices of size n with an integral inverse. These are just the integral matrices with determinant plus or minus 1, making them act on Rn in the usual way. One has the typical toral automorphism on the quotient. The fundamental group of an n torus is a free abelian group of rank n. The kth homology group of an n torus is a free abelian group of rank n. Choose k. It follows that the Euler characteristic of the n torus is 0 for all n. The cohomology ring H can be identified with the exterior algebra over the Z modules in whose generators are the duals of the n non-trivial cycles. Configuration space as the n torus is the n-fold product of the circle. The n torus is the configuration space of n ordered, not necessarily distinct points on the circle. Symbolically, Tn equals n. The configuration space of unordered, not necessarily distinct points is accordingly the orbifold Tn, Sn, which is the quotient of the torus by the symmetric group on n letters. For n equals 2, the quotient is the Mobius strip, the edge corresponding to the orbifold points where the two coordinates coincide. For n equals 3, this quotient may be described as a solid torus with cross-section an equilateral triangle, with a twist, equivalently, as a triangular prism whose top and bottom faces are connected with a 1/3 twist. The three-dimensional interior corresponds to the points on the 3 torus where all 3 coordinates are distinct. The two-dimensional face corresponds to points with 2 coordinates equal and the third different, while the one-dimensional edge corresponds to points with all 3 coordinates identical. These orbifolds have found significant applications to music theory in the work of Dmitry Timochko and collaborators, being used to model musical triads. Flat torus. The flat torus is a torus with the metric inherited from its representation as the quotient R2, L, where L is a discrete subgroup of R2 isomorphic to Z2. This gives the quotient the structure of a Riemannian manifold. Perhaps the simplest example of this is when L equals Z2 itself. R2, Z2, which can also be described as the Cartesian plane under the identifications tilde. This particular flat torus is known as the square flat torus. Its surface has zero Gaussian curvature everywhere. Its surface is flat, in the same sense that the surface of a cylinder is flat. In 3 dimensions, one can bend a flat sheet of paper into a cylinder without stretching the paper. But you cannot then bend this cylinder into a torus without stretching the paper. A simple 4-dimensional Euclidean embedding of a rectangular flat torus is as follows: equals where R and P are constants determining the aspect ratio. It is diffeomorphic to a regular torus but not isometric. It cannot be isometrically embedded into Euclidean 3 space. If R and P in the above flat torus form a unit vector less than R, P greater than equals less than cos, sin greater than nu, V, and eta can be used to parameterize the unit 3 sphere in a parameterization associated with the Hopf map. In particular, for certain very specific choices of a square flat torus in the 3-sphere S3, where eta equals pi, 4 above, the torus will partition the 3-sphere into 2 congruent solid tori subsets with the aforesaid flat torus surface as their common boundary. One example is the torus T defined by T equals S3, x2 plus y2 equals 1/2, z2 plus w2 equals 1/2. Other tori in S3 having this partitioning property include the square tori of the form Qt, where Q is a rotation of 4-dimensional space R4, or in other words Q is a member of the Lie group, so it is known that there exists no C2 embedding of a flat torus into 3 space. On the other hand, according to the Nash-Kuiper theorem, proven in the 1950s, an isometric C1 embedding exists. This is solely an existence proof, and does not provide explicit equations for such an embedding. In April 2012, an explicit C1 embedding of a flat torus into 3-dimensional Euclidean space R3 was found. It is similar in structure to a fractal as it is constructed by repeatedly corrugating a normal torus. Like fractals, it has no defined Gaussian curvature. However, unlike fractals, it does have defined surface normals. It is a flat torus in the sense that as metric spaces, it is isometric to a flat square torus. This is the first time that any such embedding was defined by explicit equations, or depicted by computer graphics. N-fold torus. In the theory of surfaces there is another object, the n-fold torus, often called the n-hole torus. Instead of the product of n circles, an n-fold torus is the connected sum of n2 tori. To form a connected sum of 2 surfaces, remove from each the interior of a disk and glue the surfaces together along the disk's boundary circles. to form the connected sum of more than two surfaces, sum two of them at a time until they are all connected. In this sense, an n-torus resembles the surface of n donuts stuck together side by side, or a two-sphere with n handles attached. An ordinary torus is a one-fold torus, a two-fold torus is called a double torus, a three-fold torus a triple torus, and so on. The n-fold torus is said to be an orientable surface of genus n, the genus being the number of handles. The zero-fold torus is the two-sphere. The classification theorem for surfaces states that every compact connected surface is topologically equivalent to A, the sphere, or B, the n-fold torus with n greater than 0, or C, the connected sum of n projective planes with n greater than 0. Toroidal polyhedra. Polyhedra with the topological type of a torus are called toroidal polyhedra, and have Euler characteristic V-E plus F equals 0. For any number holes, the formula generalizes to V-E plus F equals 2 minus 2n, where n is the number of holes. The term toroidal polyhedron is also used for higher genus polyhedra and for immersions of toroidal polyhedra. Automorphisms. The homeomorphism group of the torus is studied in geometric topology. Its mapping class group is isomorphic to the group GL of invertible integer matrices, and can be realized as linear maps on the universal covering space Rn that preserve the standard lattice zinc and thus descend to the quotient. At the level of homotopy and homology, the mapping class group can be identified as the action on the first homology. Since the torus is an Ellenberg-MacLane space K, its homotopy equivalences, up to homotopy, can be identified with automorphisms of the fundamental group. That this agrees with the mapping class group reflects that all homotopy equivalences can be realized by homeomorphisms. Every homotopy equivalence is homotopic to a homeomorphism, and that homotopic homeomorphisms are in fact isotopic. More tersely, the map homeoshi is one connected. This is if homeomorphism reduces to homotopy reduces to algebra result. Thus the short exact sequence of the mapping class group splits. So the homeomorphism group of the torus is a semi-direct product. The mapping class group of higher genus surfaces is much more complicated, and an area of active research. Coloring a torus. If a torus is divided into regions, then it is always possible to color the regions with no more than 7 colors so that neighboring regions have different colors. Cutting a torus. A solid torus of revolution can be cut with knives to show how many planes it can be cut into at most n times parts. The initial terms of this sequence, for 0 and 10, are as follows. 1, 2, 6, 13, 24, 40, 62, 91, 128, 174, 230.